Okay, good afternoon. Are you able to hear me and see the slides?
Yes, ma'am. Good
Yes,
afternoon.
ma'am.
Okay, so in the last class, we did an overview of some of the concepts, which I said would serve like a background to understand the area of this class, which is statistical inference. So today I'm going to formally begin the lectures. I'm going to use a set of lecture notes which I will upload on the class page. So I have uploaded the video from the last lecture. I hope you are all able to access it. So these are the class notes which were used in last year's lecture in case you're wondering why the name is belongs to somebody else. So this is what statistics is about. These three things. One is collection of data. So you have areas like sample surveys which teach you how to collect the data. Once you collect the data, you have to do some processing of the data and organize it into a data set. You might have to collect data from different sources and you might have to link them and create a single data set. So all this comes under compilation. And finally, you need to analyze the data and draw your conclusions. So this is a narrow definition of statistics. A broader definition is that we want to make a meaningful statement about an experiment or a phenomenon. Now, these words, experiment, phenomenon, they're all used in a particular sense in statistics. And for that, we need to understand some basic concepts. So, we touched upon some of these concepts, like that of a sample, that of a population, that of a probability distribution, and that of a sampling distribution. We will do a bit of recap on this before we make further progress. So, I pointed out in the last class that as far as statistical inference is concerned, we basically want to make a statement about a population. So if we knew the whole population, it would be easy to make this statement. You know how to use descriptive statistics. So you could, for example, calculate the population mean, the population variance, population correlations, etc. The problem is that we don't know the population. We only observe one small sample from the population, which may be a good sample or may be a bad sample. So we want to make as reliable a statement about the population as possible given the constraints of my sample. So if you remember in the last class I talked about error. Because your sample might turn out to be an unrepresentative sample, you might be measuring height, and by some unfortunate event, you ended up measuring the four tallest people in the class in your sample. So it's not an impossible event. It's possible that this might happen, and this will lead to a biased estimate. If you take the average height of these four tallest people, it will lead to a bad estimate, an unrepresentative estimate of the average height of the class. So we have to use the concept of probability distribution, which will take into account the probability of getting such samples and use some method to guard against error as best possible. I use the word experiment. So this is what we mean. We don't really mean a lab experiment. We mean any event or any phenomenon which we are interested in studying. So here are some. Maybe we want to study the heights of adult women, the number of matches won by a football team, the number of patients cured by a given medicine, the length of remaining life of a cancer patient, the increase or decrease in the air pollution levels. So these are all experiments. They all have some well-defined objective which we want to report on. So this is the first requirement of statistical inference, that you have this underlying experiment and some well-defined event which you want to make a statement about. A fundamental concept is that of a population. So when we make this statement, we have some target population in mind. I might measure 4 students from Baligan Science College. I might measure their height. But the statement I wish to make, if I'm performing statistical inference, it doesn't relate to these 4 students only. It relates to some larger population of which these students may be assumed to be a random sample. So perhaps I'm interested in all students who ever studied at Baligan Science College. Perhaps I'm just interested in all people, all adults who belong to a particular age group. So when we perform statistical inference, we assume that this target population is well defined. It might be easy to define the target population. So perhaps I'm using these 4 students as representative of all students who study at Baligan Science College. It might not be so easy to define the target population. So I might take 4 patients from SSKM hospital, measure their blood pressure, and wish to make an average statement about blood pressure of patients at SSKM hospital. So this phrase actually is not meaningful. Patients at SSKM hospital. To make a interpretable statement, I need to know who are the patients who come to SSKM hospital. So from which target population, which socioeconomic group, which diseases did this group arise? So I may or may not have prior information on this, in which case I might need to make some assumptions. But the point is that this is a concept which needs to be defined before you can make any statistical inference. So as I said, it's large, it's usually large because that is the reason we take a sample, that we are not able to measure the full population. It can be hypothetical. So all possible results of tossing a coin. You obviously don't observe all the results. So this is a hypothetical population. It can be actual, and from biological experiments or maybe physical experiments, you know that to measure certain things, so lifetime, for example, the lifetime of a bulb, it might be an experiment which is destructive, which might require you to destroy the sample unit in order to get the measurement. So these are the various types of populations. Can be real, can be hypothetical, can require a destructive experiment. But usually it is large, and the idea is that it is unobservable. It is unobservable in its entirety. Now, we next have to define this idea of a parameter. I find that often people from other sciences use the word parameter and the word variable in a different sense, in that it is used in statistics. So, when we say parameter in statistics and for this class, we will mean any characteristic of the population, anything about the population which it would be possible to measure if it was possible to observe the full population. So you have three examples here. The first example is my population is all adult Indians. My parameter is their average per capita income. The second example might be, so it's highly specific population. It's Bengali children of age 14, LBD. LBD means last birthday. So when you ask somebody age varies over time. You have to specify a point of time. We usually ask the age on their last birthday. So the parameter of interest could be their mean IQ level. So you know what these quantities mean. The mean, the variance. Per capita means that it's the income divided by the population. The third example is all wheat producing countries of the world. So it's not all countries of the world, it's all wheat producing countries of the world. And my parameter is the country specific mean wheat production in a specific time period. So in this case, I will have one parameter for each country, leading to a vector of parameters. So multiple parameters, which we organize into a vector. We defined a population. The next is the definition of a sample. So sample is that part of the population that we are actually able to observe, and hence the part of the population which we are able to study. Now we don't study the sample for the sake of studying the sample. We study the sample for the sake of making an inference, making a statement about the population. Now, you know what the science of statistics, the discipline of statistics is, but we also use the word statistic in a singular sense in our subject. We use it to mean a particular thing. So we saw that any characteristic of the population is called a parameter. Similarly, any characteristic based on the sample is referred to as a population. So we considered the entire adult population of India and their average income. This is a parameter. If we select 1,000 Indians from this population and we measure the average sample income of these 1,000 Indians, then this is called a statistic. We might measure the mean income, so that is one statistic. We might measure the standard deviation of the income, that is also a statistic. Similarly, for the Bengali children, we might select 200 Bengali children age 14 and look at the mean IQ, the median IQ, the range of IQ. We can select 25 wheat producing countries from the entire population and look at their sample mean production. Each of these are based on the sample. They're the same concept as the population parameter, but they're based on sample measurement, and hence our term for these quantities are statistic. So each of the mean, standard deviation, variance, correlation, whenever it refers to the sample, it's called a statistic. Not statistics, but statistic in the singular. So we saw this diagram in the last class. I have some well-defined target population. I might not actually have it in the sense it might not actually exist. It might be a hypothetical population. But I have this very large population, and from it, I have selected a small set of individuals. For the purpose of this class, we will assume always that these individuals are selected at random. So this means that every person in the sample has the same probability of being selected. It is possible to do inference when samples are not selected perfectly at random, but selected using some other probability scheme, but that is beyond the scope of this class. So next we come to statistical inference. As I said, we are not interested in the sample. We are only interested in the sample to the extent it reflects the population. So we're interested in this population. We have some well-defined experiment and we have some well-defined parameter which we want to make a statement about. We cannot do this because we don't observe the population. So I defined statistical inference in the last class. Statistical inference is concerned with making a decision or an inference about the population based on the sample. There is, however, good inference and bad inference. So going from the sample to the population, it can be done in several ways. For example, I can account for the fact that I might have errors. I can account for the fact that I have sample to sample variability. So if I do this, then I have what is called a good probabilistic method of inference. So if you want a broader overview, statistics is broadly concerned with these four aspects. The first, as I said, is designing your experiment. So there is an idea of design here. You might, for example, want to specify how many you want in each group. So this is when you are getting data from a lab experiment. Alternatively, you might not get data from a lab experiment. You might just observe a habit, say smoking, in a population. So this is the theme of sample surveys. For a lab experiment, you can assign one treatment to one group and another treatment to another group and compare the differences. For an observational study, say on something like smoking, you can't really ask a group to smoke, it would not be ethical. So here you don't assign anything, you just observe the whether or not a person is a smoker. So these two are the areas of design of experiment and sample surveys. The next is the study of the sample. So given a sample, without thinking about the underlying population, you have studied the area of descriptive statistics and you know how to represent a sample. So suppose you have 100 units in your sample, you don't really report the all 100 measurements. It's not possible to get a sense of the data looking at 100 measurements. It is too much information to take in. So we report certain statistics from the data. So these could be the mean, the median, the range, the standard deviation, the correlation, and so on. Next, we come to statistical inference. And for that, the prerequisite is the area which is mentioned first, which is probability and distributions. As I said, there is good inference and bad inference. And to make sure that we are making the most scientifically sound inference possible, we need to go into a probabilistic framework and use the concept of probability distributions. I gave you some examples of variables. So another important distinction in statistics is that between different kinds of variables. So we distinguish between qualitative and quantitative variables. So I gave you the example of weight. Weight is a variable which can take any value in a certain range. Such a variable is called a quantitative variable. Alternatively, we can have variables like color, opinions. So these don't have numerical values. They they can assume one of two categories, one of a certain number of categories. So for smokers, for example, you can think of never smoked, smoked in the past but not current smoker, current light smoker, current heavy smoker. So these are four categories. The variable smoking, it would assume one of any four of these categories. So these are called categorical variables, and these are treated entirely differently from numerical variables like weight. A particular case of categorical variables which is of interest, you might have heard of techniques like logistic regression. They're applicable when you have binary categories. So binary means a variable which can take one of two values. So you might simplify the smoker into never smoked and everyone else who is classified as a smoker. We distinguish between continuous variables. So continuous variables are height, weight, temperature, etc. So these variables are characterized by the fact that they can take any value in a certain range of values. A discrete variable, it can't take any possible value. It takes only a set of distinct values. So the number of goals in a football match, it can be 0, 1, 2, etc. The number of patients admitted to a hospital, similarly, it must be an integer valued variable. So inference will depend on the type of variable. So here is an example to motivate the introduction to probability. Suppose we are tossing three coins. The, so I said that the first starting point needs to be an experiment. My experiment is that I am tossing three coins. So what are the possible outcomes? The first outcome is that all three are heads. So H, H, H. The next is that the first two are heads, the second is a tail. So H, H, T. Similarly, the first and third are heads and the second is tail. So H, T, H. So on, I can distinguish between 8 possible categories. So this is my experiment and this is my population. The next thing I need to do is to define my parameter. So let me define my parameter as a probability and let me assume that this probability pi, I use the Greek symbol pi to denote probability. It is a common practice in statistics to use Greek symbols to denote population parameters. In the last day, we saw that the normal distribution, the mean of the normal distribution is typically denoted by mu, and the variance in the normal distribution is typically denoted by sigma square. So let pi be the probability of head the probability of observing a head in a single toss. Now, what do I observe from my experiment? I have to define some variable. So let me assume that I observe this quantity, which I've denoted by x. Usually we use these symbols like x, y, z to denote the variable which we observe, and we call this a random variable. So my random variable x here is the number of heads in three tosses. So how many heads could there be in the three tosses? There could be 0. So there could be 0 if each of the tosses results in a tail. So what would be the probability of this outcome? You have this table here which gives all possible values of x, the corresponding experimental result which would generate this value, and the probability of this value occurring. So let us consider the last value first, which is 0. If we assume that each toss of a coin is independent, you would have covered the concept of independence in your probability class. If not, it means that the result of one toss does not depend on what happened in another toss. So in that case, we have that the probability of head is pi. Now tossing a coin, it either results in a head or a tail. So if the probability of head is pi, it means that the probability of a tail must be 1 minus pi. So what is the probability that I observe a total of 0 heads in 3 tosses? I have to first observe a tail in the first toss. The probability is 1 minus pi. For the second toss, it is again 1 minus pi. And for the third toss, it is again 1 minus pi. Because the events are independent, I can multiply the probabilities. I can multiply the probabilities and come up with 1 minus pi to the power 3. So 1 minus pi into 1 minus pi into 1 minus pi. In how many ways can I get all 3 tosses resulting in head? So in how many ways could I get x equal to 3? I would have to have a head in each of the 3 tosses, and by the same logic, the probability of this happening is pi cubed. So just like the probability of x equal to 0 is 1 minus pi whole to the power 3, the probability of x equal to 3 is pi cubed. So what about observing x equal to 2? So look at all the 8 possible results and count out the ones where x is equal to 2. So these are HHT, HTH, and THH. So what is the probability of HHT? I would have to have pi, the probability of the first head is pi, multiplied by the probability of the second head is also pi, multiplied by 1 minus pi, which is the probability of the third tail. So the probability of HHT is pi into 1 minus pi, which is pi square into 1 minus pi. Similarly, if we look at HTH, the probability is pi into 1 minus pi into pi, which is again pi square into 1 minus pi. And similarly for the third case, so we can add all 3 and get that the probability of observing x equal to 2 is 3 pi square times 1 minus pi. Similarly, I will leave it to you as an exercise to calculate the probability of x equal to 1. So now let us ignore the middle column and just look at the first column and the last column. So these 2 columns of the table, they give the possible values of x. X is my random variable, which I defined as the number of heads in 3 tosses of a coin. So the values of x are 0, 1, 2, 3, and the last column of the table gives the probability that x takes value 0, x takes value 1, x takes value 2, x takes value 3. You can check that if you add up all the four probabilities, you will get 1. So x must take a value of either 0 or 1 or 2 or 3. And because these events are exhaustive, the total probability must be 1. So the first and the third column of x, they define what is called a probability distribution. This is an example of a probability distribution of a random variable. Now x in this case you can see is discrete. So this last column of the table, it specifies what is called a probability mass function. So you can see that the heading of the third column is probability capital X equal to small x. Now capital X we usually use to denote some random variable. Small x we use for specific numerical values. So probability capital X equal to 3 is pi cubed. Probability capital X equal to 2 is 3 pi square into 1 minus pi, etc. That is how you would read this table. The collection of all values small x and the corresponding probabilities. If x is discrete, it is called a probability mass function. We also saw some variables which are not discrete but are continuous. If x is continuous, then if you remember in the last class, we saw the example of a normal distribution. We applied it to the weights of the US population. Weight is an example of a continuous variable. In case of a continuous variable, we drew the normal distribution. So the function which we drew, if the underlying variable is continuous, it is no longer called a probability mass function. It is called a probability density function. So we will come back later to probability density function. It will be the main topic of this class. So here we have another fundamental concept, which is that of a frequency distribution. Now my experiment was that I tossed 3 coins 200 times. Out of these, I'm looking at my observed frequency of observing 0 heads, 1 head, 2 heads, and 3 heads. It turns out that out of the 200 tosses, 28 resulted in 0, 51 resulted in 1, 73 resulted in 2, and 48 resulted in 3. The second column gives the actual frequencies, the third column gives the relative frequency. So this is my sample version of the probability distribution. On the previous slide, not on the previous slide, before this. So on this slide, I assume some hypothetical actual probability pi, which relates to the parameter, the underlying population parameter, which I don't know. And I derive the population values for the probabilities 3, 2, 1, 0, etc. So suppose I don't know pi, then the best thing I can do is to do an experiment of this sort and observe how many times I have each of these outcomes, 0, 1, 2, 3. So as compared to my previous slide, this is based on my sample. So in the previous slide, we had probability. Here, my last column is the relative frequency. The relative frequency is the sample version of the probability. It's your best guess for the underlying population probability if you don't know it. The problem of inference here would be to try and guess the value of pi based on this observed data. So, any questions? So, we will define some fundamental probability distributions. The first is that of a binomial distribution. So, this is how a binomial distribution arises. We have to have some experiment which results in one of two possible outcomes. So, one, for example, could be the one we saw in the previous set of slides, which is that of tossing a coin. So, tossing a coin could result in either head or tails. So, we arbitrarily call the head the success or tail the failure. It does not really matter, you can label it otherwise. Similarly, we can be trying to count how many smokers there are in my sample. So if someone is a smoker, I call it a success. If someone is not a smoker, I call it call that event a failure. The idea is that you have some experiment which can result in any one of two values. In statistics notation, we term these two values success and failure. It doesn't really relate to the sense in which we use success and failure in English language. It is up to you to define which event you want to call the success and which event you want to call the failure. We aren't going to perform this experiment once. I'm going to assume that we perform it n times. So, like in the previous experiment, I tossed my coin 3 times. So, for that example, my n was equal to 3. So, I have some experiment. Each repetition of the experiment can result in any one of two outcomes. I label these success and failure. I repeat this experiment n times and I make one key assumption. I assume that the trials are independent. Now, you should know what is meant by independence in a statistical sense from your class on probability. For the experiment of tossing a coin, it means that if you get heads in a particular coin, it does not affect your probability of getting head in another toss of the coin. So the outcome of one toss in no way influences the outcome of another toss. Similarly, you would assume that the chance of getting a smoker, the first person being a smoker in your population, it does not affect the probability of the second person being a smoker. We can assume that something like this will be a reasonable assumption if we have collected the data at random. So we make this key assumption that we have in what are called independent trials. By trial, we mean one repetition of this experiment. So again, to repeat, we have an experiment which can result in one of two outcomes. At our discretion, we label these two outcomes as success and failure. We repeat this experiment for some pre-specified number of times. We call this number n. We have to make one key assumption to get the binomial distribution. This key assumption is that the n trials are independent. By trial, it is our terminology for one repetition of the experiment. So this is my experiment of interest. I have to define some parameter and I have to define some random variable. So let me assume that my parameter, so again I said that we usually use Greek notation to denote parameters. Anything related to the population, we typically use Greek notation for this. So in this case, suppose that my parameter of interest is the probability that a particular trial results in success. We are assuming that the trials are identical. That is, we are assuming that the probability of success happening in the first trial is the same as the probability of success happening in the second trial, the third trial, or any one of the trials. So let us suppose that this common value is pi. So as said here, pi is assumed to be constant for each trial. What is the variable which I am observing? I am only observing the total number of successes in the n trials. So if you go back to the example, we looked at the detailed example and presented it in a table. We are not observing the middle column. We are only observing the first column, which is the value of x and the corresponding number of times it happens in a sample. So x is the number of successes. We are going to define the binomial probability distribution. So the random variable x is said to have a binomial distribution if it has the probability mass function which is given here. So this means that f of small x. So let me assume I want my random variable x is the number of successes in the n trial, and I want the probability that there are no successes in the n trials. So every one of the trials resulted in a failure. The way to calculate this would be to note that no successes means that small x is equal to 0. So I have to plug in small x equal to 0 in the expression given here. You will see that f of 0 is n choose 0, which is 1, pi to the power 0, which is also 1, times 1 minus pi to the power n minus 0, or 1 minus pi to the power n. So you can go back and compare this to our example of tossing the coin 3 times, and see that there we got the expression 1 minus pi to cubed. So it's not just true for that particular experiment, it is true for any n repetitions of similar experiment where you can have two outcomes, and this is called the binomial distribution. Similarly, say if I want the probability that x is equal to 5, I observe 5 successes in n trials, then I have to calculate the value of f5. So this is equal to n of n choose 5 times pi to the power 5 into 1 minus pi to the power n minus 5. So note that small x can only take value 0, 1 up to small n. This distribution is called the binomial distribution. We saw in the last class the example of a normal distribution, and we saw the similar kind of notation. So to denote a normal distribution with mean mu and variance sigma, we use this funny symbol tilde. It's on the upper left hand side of your keyboard. So our notation there was x tilde n mu sigma square. This means that x is a random variable which follows a normal distribution with mean mu and variance sigma square. Similarly, for the binomial distribution, we will say x tilde binomial n pi. So x tilde n pi, it means that x follows a binomial distribution where the total number of trials is n And the probability of success in any trial is pi. We define two characteristics of this probability distribution. One is the mean value of the probability distribution. So note, this is not a sample mean, it's a population mean. Our notation for sample mean, our notation for population mean is E. E denotes expectation. So E of x is n pi, which means that if it was possible to observe the full population, the average value of x would be n pi. So this kind of makes sense intuitively. If you have a single trial where the probability of success is pi, if you have n trials, on average you would expect n pi successes. Similarly, it's possible to show that the population variance of x, note I'm talking about the population variance, is equal to n pi times 1 minus pi. If n is equal to 1, we have only one repetition of the experiment, then the expression fx, it becomes just pi to the power x, 1 minus pi to the power 1 minus x. And note that x here takes only two values, 0 or 1. So this is a special case of a binomial distribution, and it's called a Bernoulli distribution. We next define what is called a negative binomial distribution. My setup is the same, that I have a trial which can result in any one of two outcomes, either success or failure. The trials are assumed to be identical, which means that the probability of any trial resulting in success is assumed to be some constant value pi. The trials are also assumed to be independent, meaning that the outcome of any one trial does not affect the outcome of any other trial. In the previous example for the binomial distribution, the variable we looked at was the number of successes observed in small n trials. So suppose small n equal to 5, the number of successes observed in 5 trials. So there we fixed the number of trials, and what we allowed to vary was the number of successes. The negative binomial distribution is a similar concept, except that here my random variable x is the number of trials required to get some specified R successes. So suppose R is equal to 5, it means that x is now the number of trials required to get 5 successes. So minimum possible value of x is obviously 5, could be 6, could be 7, could be 8. So the difference between the binomial distribution and the negative binomial distribution is that for the binomial distribution, we fix the number of trials and we observe the number of successes. For the negative binomial distribution, we fix the number of successes which we want to observe, and we see how many trials it takes to observe that many successes. The probability mass function is given here. It is very simple. It's very similar to the binomial distribution and not really that difficult to derive. So it's not necessary for you to derive it. But if you are interested, note that suppose capital X is equal to some value small x. So that means that it took small x trials. So when we say number of trials, we mean minimum number of trials. So it means that it took a minimum of small x trials to get R successes. So this can only happen if my first x minus 1 trials resulted in R minus 1 successes. So what is the probability of this? So this is again related to the binomial distribution. I have a total of x minus 1 trials and I observed r minus 1 successes. So you can plug in the binomial PMF and get x minus 1, choose r minus 1, pi to the power r minus 1 times 1 minus pi to the power x minus 1 minus r minus 1, which is the same as x minus r. So I get r minus 1 trials in the first x minus 1. I get r minus 1 successes in the first x minus 1 trials, and then the xth trial, it must result in success. So the probability of that is pi. If I multiply out the two expressions, which I can do because the trials are independent, I get the PMF, which you observe here. Like but special case of the binomial distribution was the Bernoulli distribution. Bernoulli distribution occurs when we only repeat the experiment once. So similarly, we also have a special case of the negative binomial distribution, which occurs when we are looking at the number of trials required to get the first success. So my small r is equal to 1. So in that case, the probability becomes x minus 1, choose 1 minus 1. So x minus 1, choose 0, which is 1. Pi to the power 1, 1 minus pi to the power x minus 1. So basically 1 minus pi to the power x minus 1 times pi to the power 1, and x can be 1, 2, etc. This distribution is called the geometric distribution. It's the special case of the negative binomial distribution when we're looking at the number of trials required to get the first success. So I hope you understand the difference in the experiment which generates the binomial distribution and the negative binomial distribution. For the binomial distribution, we decide that we will toss the coin n times. So say n is equal to 10. We decide that we will toss the coin n times. We stop at 10 tosses, and then we see how many successes we had, maybe how many heads we had in tossing the coin. For the negative binomial experiment, I keep tossing the coin. So 1, 2, 3, however many times it takes. I decide instead on the number of heads which I want to observe. So maybe I want to observe 15 heads. My random variable now is the number of tosses, and I'm going to keep tossing until I get 15 hits. So we also have the expressions for the two corresponding probability mass functions. It's not necessary for you to be able to derive the probability mass functions. However, they're not also particularly difficult to derive if you understand the basic idea, underlying ideas of probabilities, and the idea of independence. There is another discrete distribution mentioned here, which is the hypergeometric distribution. So when does the hypergeometric distribution come? It comes when we are sampling from a finite population. So the way it came in probability is to assume that we have an urn, say, which contains capital N cards. Of these, M are of one type, we call them S cards, and the remaining N minus M are of another type, we call them N cards. So we have a total of capital N cards in an urn. Of these, M are of one type, so you can assume maybe that M are queens, and the remaining N minus M are kings. My random variable X is then the number of cards of any one type. So let me suppose that I'm interested in the number of queens I get in my sample. The corresponding probability mass function is the one which is given here. Again, if you understand the basic concept of probability, it is not difficult to derive. So this distribution is another common distribution in statistics. It's called the hypergeometric distribution. It's not necessary that you have to be drawing cards from an urn. The idea is again that you have a population where each unit in the population is one of two types. So just like the binomial distribution and the negative binomial distribution dealt with a binary event, here too we are dealing with a binary event. So each draw from the urn can either result in a card of type N or a card of type S. So you can generalize this to assume that each repetition of the experiment can either result in a success or a failure. The difference with the binomial distribution is that the population from which you are drawing is finite. So maybe I have this population of smokers and non-smokers, and in the population I have 100 smokers and 100 non-smokers. Then obviously the number of draws of smokers, it can't go above 100. And if I'm drawing a sample from this population without replacement, the fact that we have a finite population means that the relevant probability distribution will be the hypergeometric distribution. Similarly, just like we had the negative binomial, where we fix the number of successes and let the number of trials vary, we can also have the inverse hypergeometric, where we do the same thing, the only difference being that we are now sampling from some finite population without replacement. So we are not replacing the unit which is sampled. Once it's drawn, we remove it from the population before sampling the next unit. The next very common distribution is the Poisson distribution. We have seen different types of variables. We saw that when my random variable x is something like height and weight, one relevant distribution is the normal distribution. When we have some underlying binary experiment, my relevant random variable, it could either be a binomially distributed random variable, or it could be a hypergeometric, or maybe the special cases like Bernoulli or geometric. Now let us consider a slightly different kind of random variable. Say we are looking at a particular traffic intersection in a city, and we are observing how many accidents occur at that intersection in a month. So conceptually, this is a random variable. It's obviously not a continuous random variable. It's discrete. It is not, however, a binomial variable because it doesn't take one of two values. So what values could a variable like this take? Conceptually, it could take values 0, 1, 2, etc., any positive, any non-negative integer value. If you have a random variable which is non-negative integer valued, the most common probability distribution for such random variables is the Poisson distribution. Typically, the Poisson distribution comes when we observe the number of counts of some event occurring. So maybe we are looking at the number of accidents which happen at a traffic intersection. Maybe we are looking at the number of misprints in a book. We could be looking at the number of patients of COVID who turn up at a particular hospital. In each of these cases, uh, we are trying to measure a random variable, which is the number of a certain specific event of interest happening. More common examples of this kind of event are when we look at demographic characteristics like mortality, fertility, deaths, and so on. So, in this case, birth, death, etc., would be considered the event. And if we were to model this in a probabilistic framework, we would be looking at the number of births, the number of deaths, and the relevant random variable. One possible choice for the relevant random variable would be the Poisson distribution. There are more complicated distributions for count variables. It is not necessary that every count variable has a Poisson distribution, but that I think is beyond the scope of this class. We will assume that count variables are distributed having a Poisson distribution. So we saw that any random variable, to specify the distribution of the random variable over the population, we have to specify the probability distribution. So what does this mean? For the discrete random variable, it means that we must specify the probability mass function. So this page gives you some examples of a Poisson type of random variable. My random variable x is the number of counts of an event. There are 4 examples of counts. I could count the number of particles, so maybe the number of particles emitted by some radioactive source, the number of road accidents, in the number of visits by a patient to a doctor, the number of rivers in a country. So for each of these examples, what is common is the outcome we are observing all relates to the number of some event happening. So note that for the first example, we have said that in a given time period. Similarly, when we say road accidents, we are saying that it's on a given road and in a year. So we are assuming that when we make this experiment, there is some underlying fixed concept of time. So I might repeat this experiment. When I'm saying road accidents, how many road accidents occur? It doesn't really make sense to make this statement without saying what time period I am considering. So I will assume that I have some specific time period in mind and that this time period is constant over my experiment repetitions. If this time period is not constant, then the values I get are not comparable. So if on the first day I have measured over an area of 5 square kilometers, and if on the second day I have measured over an area of 100 square kilometers, then the two observations are obviously not comparable and they can't be considered to be identical repetitions of the same random variable. So when I have this Poisson random variable, I have some underlying idea of the size or the time period to which this count relates. And I assume that this size remains constant over time and over space, over repetitions of the same experiment. If it does not remain constant, there are advanced statistical methods to take this into account. But again, these are beyond the scope of this class. So we will assume that we have some specific time period or we have some specific geographic area in mind and be concerned with the repetition of some event either over time or over space. So this is obviously a discrete random variable, and we saw that the way to specify a discrete probability distribution is to specify the probability mass function for that distribution. So this is what the probability mass function for the Poisson random variable looks like. Suppose we want the probability that the random variable capital X, it takes the value small x. This probability is given by, now again, as I said, we use Greek parameters, we use Greek letters to denote population parameters. So fx equal to e to the power minus lambda times lambda to the power x divided by x factorial, and x can take value 0, 1, 2, etc., any positive, non-negative integer values. The notation for this is x tilde p and then within bracket lambda. So x tilde p lambda, it will mean that x is a random variable which follows the Poisson distribution, and the parameter of this Poisson distribution is lambda. So what really is lambda? It turns out that the mean of the Poisson distribution is lambda. The variance of the Poisson distribution is also lambda. So this particular distribution, Poisson distribution, it has this characteristic that the mean and the variance are equal, and they are equal to this common value, which is lambda. Now, if you want, you can go back to the binomial example and look at the expression for the mean and the variance and check if it is possible to say anything about the relationship of the mean and variance when we have a binomial distribution. So for the binomial distribution with parameter n and pi, the mean is given by n pi, n times pi, and the variance is given by n times pi into 1 minus pi. Now, as 1 minus pi is less than 1, it follows that the variance must be less than the mean. So these are two properties of the binomial and the Poisson distribution. For the binomial distribution, the population variance is typically smaller than the population mean. For the Poisson distribution, the population variance and the population mean are equal, and they can be shown to be equal to lambda, which is the parameter occurring in the probability mass function. Moving on to continuous random variables, and we come to the most common continuous random variable, which is the normal distribution. So I said a continuous random variable is identified by the fact that it takes any value within a specified range. For the normal distribution, in theory, the range is infinite. So the normal random variable can take any value between minus infinity to infinity. Now we use the normal distribution to model weight in our previous lecture. So you might think that weight doesn't really vary from minus infinity to infinity. So the point is that the normal distribution has a particular shape, which we call the bell shape. And even though theoretically it lies between minus infinity to infinity, in practice, the probability of taking very large or very small values is so small for the normal distribution that we can use it to model continuous variables which only take values within certain range. So we say that it varies from minus infinity to plus infinity, but the effective probability of it taking a very large value to be almost minus infinity is practically zero. So that is why it is feasible to use the normal distribution to model most continuous random variables. So this happens because of the shape of the normal distribution. This shape is called the bell-shaped distribution. So the probability distribution for the PDF, we said that if we have a discrete variable, we have a probability mass function. If we have a continuous variable, we have a probability density function. The probability density function of the normal distribution is often referred to as the normal curve or the bell-shaped curve. So this is the characteristic of the normal distribution, that is, it is bell-shaped. The resulting property of the normal distribution is that it is very unlikely to get outliers in your sample. So if you have a sample where many of the values seem to be outliers, which is they don't seem to resemble each other at all, they seem to be at one of two extremes, then it means that your underlying probability distribution is probably not normal. So let x be some continuous random variable. In theory, we will assume it takes values from minus infinity to infinity. Examples, we saw the example of weight. We can also have height. We also saw the example of IQ. Anything else? It says measurement error here. Now, the normal distribution, it originated in statistics from the study of astronomy. And the idea of as a distribution which is relevant when you are performing an experiment repeatedly, and each repetition of the experiment doesn't result in the same identical reading. It doesn't result in the same identical reading because there is an amount of measurement error. So today such concepts may be obvious, but to recognize this existence of a measurement error as a random phenomenon, it was one of the fundamental discoveries which led to the formulation of the normal distribution. So that's why it mentions specifically measurement error as being something of historical importance, which has been assumed to be normally distributed. If you later go on to study more advanced statistical topics like regression, you will see that there is a concept of an error, and the starting point is always that we assume that such errors have normal distribution. So the normal distribution is a popular choice for modeling any kind of error. The probability density function of the normal variable, it has this particular form. F of small x is equal to 1 over sigma times square root over 2 pi times e to the power minus a fraction which has x minus mu whole square in the numerator divided by 2 sigma square in the denominator. So the expression might look complicated to you at first look. It turns out to be a probability density function of a particularly well-behaved and common probability distribution. The notation for this is x tilde n, capital N, and within brackets mu sigma square. This means that the random variable x follows a normal distribution whose mean is mu and whose variance is sigma square. So you can see on the last two lines of this slide, it says that E of x, which means the population mean of x, is mu. And similarly, the population variance of x is sigma square. Now, for the probability mass function, we saw that f of x was f of small x. It was the probability of the random variable capital X taking the particular value small x. So if I calculate the value of f at 5, it means what is the probability that my capital X takes the value 5. So this only holds for discrete random variables. This is the interpretation of the probability mass function, not of the probability density function. So for those of you who come from slightly mathematical backgrounds, it's not really central to this class, but you will appreciate that if you have a continuous random variable, it is not really possible to assign a positive probability to a particular mass, to one particular mass, because if you did, then the area under the curve, which is the total probability, cannot possibly integrate to 1. So just like a probability mass function, we saw it for our toy example. Just like the probability mass function, it must sum to 1 because we are talking about a set of exhaustive events. For the probability density function, the area under the curve, it has to integrate to 1. In fact, the interpretation of the probability density function is not the probability that x takes any particular value. The probability density function is used in the way which is indicated on this curve. So this is the normal bell-shaped probability density function. You can see the notation x tilde n mu sigma square. The central point is mu. I told you on the last day, and you can see it on this slide also, it is symmetric about mu. We have 2 points marked on the x-axis. One is the point mu plus 1.96 times sigma. The value 1.96 is important. We will see later why. And similarly, by symmetry, we have a value which is at an equal distance below mu, and it is mu minus 1.96 sigma. So how do we use this curve? Suppose I want the probability of x being larger than the value mu plus 1.96 sigma. So suppose my mu is 0 and my sigma is 1. This means that I want the probability that x is larger than 1.96. So the way to get it is to mark the point mu plus 1.96 sigma on the x-axis, draw the vertical line from that point up to the curve, and then calculate the area of the shaded portion you see on the curve. It turns out that this value is 0.025. By symmetry, the probability of in the lower tail below mu minus 1.96 sigma is also 0.025. So this value 0.025, it is the probability of x being greater than mu plus 1.96 sigma. It's also the probability of x being less than mu minus 1.96 sigma. The point is that given any probability distribution function, the way to use that function is to calculate the probability of x lying in any particular range. So for this example, say, if I wanted the probability of x lying between 3 and 5, I would mark off 3 on the x-axis, and I would mark off the point 5. From each of the points, I would draw vertical lines up to the point where it meets the curve, and then I would have to calculate the area of the figure which is generated in this way. This area can be interpreted as the probability of x lying in between these two values, in this case 3 and 5. So that is the interpretation of the probability density function. So in the interest of time, I think let me stop here for today, and I will continue with these slides on the next day. So do you have any questions?
ম্যাম বলছি যে আমি
Yes.
না ক্লাসরুমের ইনভিটেশনের লিংকটা পাইনি, আমি কি আপনাকে একটা মেল করে দেব?
হ্যাঁ, করে দাও।
ম্যাম আমিও
তুমি কি
পাইনি।
অরিজিনাল লিস্টে ছিল? তোমরা কি অরিজিনাল লিস্টে ছিলেন? আমার কাছে একটা লিস্ট ছিল, আমি সেটাতে
হ্যাঁ ম্যাম,
হ্যাঁ, ঠিক আছে।
ক্লাসের লিংক পেয়েছি, কিন্তু
ম্যাম কোনো ক্লাসরুমের কি লিংক পাঠিয়েছেন আপনি?
ক্লাসরুমের লিংক তো অটোমেটিক্যালি যাওয়া উচিত। তোমরা কি ক্লাসরুম কেউ অ্যাক্সেস করতে পারছো না?
ম্যাম কোনো ক্লাসরুমের লিংক পাইনি ম্যাম, আর বাকি মেল পেয়েছি আপনার থেকে, কিন্তু ক্লাসরুমের কোনো লিংক পাইনি।
বাকি মেল মানে কি পেয়েছো?
মানে ম্যাম ক্লাসের লিংকটা পেয়েছিলাম আগের সপ্তাহে যেটা পাঠিয়েছিলেন, কিন্তু ক্লাসরুমের কোনো ইনভিটেশনের লিংক পাইনি।
আচ্ছা, পাওয়া উচিত তোমাদের। ঠিক আছে, আমি গিয়ে চেক করবো। তোমরা যারা ইনক্লুডেড নাও, তারা তোমরা কিসে ইনক্লুডেড নাও? এই মিটিংটাতে ইনক্লুডেড নাও নাকি ক্লাসরুমে ইনক্লুডেড নাও?
ম্যাম ক্লাসরুমে।
ম্যাম ক্লাসরুমে নেই।
ঠিক আছে, তাহলে ক্লাসরুম থেকে ক্লাসরুম তো ক্রিয়েট করেছি আমি, ক্লাসরুম থেকে তাহলে কোনো কারণে ইনভিটেশনটা যায়নি, আমি দেখছি।
ম্যাম আরেকবার একটু তাহলে সেন্ড করে দেবেন।
হ্যাঁ।
ওকে ম্যাম, থ্যাংক ইউ।